So here is a live PC that is based on the Windows operating system and whose architecture is built around LPDDR5 memory. So as you can see, this is a live Windows operating system. We can run any application we want here. But what's special about this particular PC is that we are probing it live with the Introspect LPDDR Protocol Analyzer. So I'm showing the logic board for the PC here. And of course, of particular interest is the LPDDR5 memory. This is a 315 ball standard package LPDDR5 memory. And here it is sitting on top of the Introspect technology integrated tip interposer. This kind of interposer provides solderless access to all signals under the memory. So here we're showing the DQ signals in this green cable assembly and the ACA signals in the blue cable assembly. And because it does not require any soldering and everything is embedded inside the connector, you get very high signal integrity and very low noise coming out of this interposer. The signals coming out of the interposer are going to two RSH devices. These are remote sampling heads, and they are active probe solutions that provide access to 12 channels simultaneously. In this particular demo, we're showing two of them. One, like I said, is connected to the DQ bus on the green assembly, and the other is connected to the CA bus on the blue cable assembly. The output of the RSH is just like any active probe solution, so it can go to an oscilloscope or it can go to the Introspect technology M7030 DDR LPDDR Protocol Analyzer. This is the latest product from Introspect technology, and it addresses the highest speed applications for memories with a high sampling rate, with advanced features like supporting clock stops and clock frequency changes, and unterminated CA operation, as well as nested triggers and nested commands for different applications. So now we have moved to my PC where I have Pine-Tree open here. And by way of introduction for Pine-Tree, of course, it's our development environment that works with all of Introspect's test equipment. And fundamentally, it's a Python interpreter. So the main window here is a Python editor where you can enter any Python command, including if and for statements and dictionaries and so on. And so what we have done at Introspect is we have created Python classes that represent the hardware, that represent the analyzer that you are using. And in this particular case, one class is called the analyzer calibration class, and another class is called the data capture. These classes have methods associated with them, just like the run method that I'm showing here. They also have attributes or properties that you can assign. And so in this case, I'm assigning a result name called test_tiny_pc. These attributes are available through Python, but they're also, for the most part, available in the GUI through this pane that I just opened right here. So you can imagine the attributes for the capture component being, including things like the receiver channel list. So this is the list of channels that you want to probe, basically, with your analyzer. And as a convenience method, we have created a component class called DDR channel labeling that maps basically the interposer signals to the analyzer pinout. So if you look at this table, for example, here, the signal CK is connected to channel 5 on the analyzer, the signal chip select 0 is connected to channel 4, and so on. So once you have these labeling components available, you do not have to worry about pin position on the analyzer. You just worry about the signal names which are coming from your package and your protocol. What's more actually is that the interposers, with the standard interposers that Introspect has created, you can also have pre-populated channel labeling components like this, so that you can just reference the interposer and you'll know that the pinout on the analyzer is already pre-configured for you. There are other attributes in the data capture component, for example, like trigger options, where you can trigger on different commands. You can trigger on sequences of commands, or you can even trigger on custom commands where you create your own truth table combination and you ask the analyzer to trigger on it. For now, I will leave everything as default, and then I will do a quick run on the analyzer to see what that PC is doing. So the capture has already ended, and now in my result icon here, I have a notification saying there's a new result. I will click on it and open the viewer. And then here we see now basically what the PC is doing. What we have done to enable this application is since it's a Windows application, we wrote a small script on it to do a bit of a stress test on the memory. And so you'll see a lot of write commands, you'll see a lot of read commands, and that's just to stress the memory and take it through its paces. So you can see the memory is running at 5.2 gigabits per second in this case, and you see every command that's being sent. So activate commands are visible, write commands are visible, and then at the top, I think I've shown you some read commands, pre-charge commands available here as well. And so every time we click on a command, we would see the arguments associated with that command available in the row that we have highlighted. But also on the left, we can see also the arguments in the table that's listed on the left-hand side here. So the analyzer basically decodes the truth table and gives you a human readable way of understanding what commands are being sent. And then at the bottom left here, you will see a timing analysis basically to tell you if something is in violation or not. And so if we go to the top here, I think there was already a couple of warnings where things seem to be a bit too close. So for example, this particular write 32 command, there is a warning where the spacing to the next read 32 is a bit too close. So command number 12, which is read 32 here, comes after 40 NCK instead of 42 NCK as defined by the specification. So this would be a real violation that we have observed here. I can go to the waveform for the write 32 and just like try to observe what really has happened here. So this is my write 32 edge. And then if I just keep zooming out, without losing my bearing here, you'll see that the write 32 edge that I had was somewhere here as identified by these faint gray markers. And then the timing under issue here is the second read 32 command seems to be too early, right? And so this is just the analyzer counting the number of CK cycles between these two commands and saying that there could be a timing violation here. And so this was just a quick view of how a capture is run. If I close this and run another time, it'll show you this concept of scripting, right? So every time I click run, the script is executed again the same way, and I will get a new result object here, and I will open it. And you'll notice that the trace now starts differently because in my trigger options, I haven't really declared anything, which means I'm just going to trigger on any chip select that I see. If I trigger specifically on a pre-charge, let's say, or on an activate one command, then I will always see the beginning of the trace being the trigger command that I asked for. And the reason is that the analyzer is always actually monitoring the traffic in hardware and understanding the commands that are coming in. And when you trigger on a certain command, the analyzer just freezes that capture window around the command that it sees. So there is hardware processing that is happening here. And what the viewer is giving us is basically just a snapshot of the traffic that's been received by the analyzer. So in this case, again, we're seeing a section of write and write operations. I'll click on the activate command just to show it. For those of you who are familiar with the activate command, this is very evident here in this waveform. But I'll also go to maybe show you some of the DQ lines. So I'll add a couple of DQ lines to this particular trace just to show again the traffic. And so you can see now the DQ is running at the speed of WCK, so it's very fast, and that's the biggest advantage of this analyzer is that its sampling rate is so high that it can capture DQ on LPDDR5 and even LPDDR6 applications. And then finally, something that I haven't showed you in the last run is this analysis tab, where you get statistics of the commands that you have received with the analyzer, as well as timing histograms as well for the different timing parameters that have been analyzed by the tool. So this is where a lot of the analysis, your analysis happens. You want to know what your system is doing and what your controller is doing to the memory, essentially. So all of these timings are measured and displayed. They are displayed here graphically, but of course, they're also available in Python, and they're also available in the file system as files, either JSON files or raw files that you can retrieve and analyze yourself. And again, as mentioned, most of the traffic here is write traffic. That's just by virtue of the stress test that we've created. And you can see the different rank operations as well.